let's check the energy balance. In the big ideas in FEA, we saw that from the discrete equation at the essential boundary condition, we were able to calculate the reaction, and that involved the heat flux at that node times the area of that phase. And that was step 3 in the finite element procedure. And so that's what we will do. We'll calculate the reactions. And here, the reaction will involve, you need an area. So for that, you need not only this length here, but you also need the dimension perpendicular to the screen, and that's given by the thickness. So if I go to surface body, and the thickness is 1 by default, so you can think of whatever reaction you'll get along here is the heat flow through that boundary per unit thickness. So let's calculate that reaction at that essential boundary condition. So I'll highlight solution in the tree, and I'll say probe reaction, and I'll pick my temperature boundary condition, and I will say this is, and I'll say evaluate all results. And that tells me that the heat flow, the net heat flow through that boundary is 1.67 watts, and the direction is into the domain, so that it's taking as positive. And it turns out, you can also get a reaction at the convection boundary condition, which we haven't talked about. Convection is a more complex boundary condition because it involves both the temperature and its gradient. So let's just use the facility in the code to calculate the reaction there. So I will highlight solution, say probe, reaction, and then pick the convection boundary condition and say evaluate all results. And that's negative because the heat is flowing out through that boundary, as we can check with the heat flow. Under the heat flux vector. So you have heat coming in, heat going out. There's no heat crossing the other two boundaries, and there's no heat generation. So this has to balance that. And if I look at that value, that balances the heat coming in. So that's a check on the aggregate energy imbalance. We saw that doesn't mean that energy is conserved for each infinitesimal element, or it's conserved for each finite element. It just means that it's conserved in aggregate. But that's a very important check to do.